seek to describe a reality that exists sans observers. But there is one reality life draft that we haven't touched on this show, and that's superdeterminism. It may have the most disturbing implications of all. Erwin Schrödinger, co-inventor of quantum mechanics with Werner Heisenberg, was a big proponent of realism. In fact, his alive and dead feline thought experiment was a reductio ad absurdum designed to highlight the ridiculousness of extrapolating observer-dependent indeterminacy to large or macroscopic objects. Albert Einstein also came up with a scenario in which he tried to refute the non-realist implications of pure quantum mechanics. Along with Boris Podolsky and Nathan Rosen, he proposed the EPR paradox, which was meant to deal a swift death blow to this observer-centric nonsense. We've talked about the EPR paradox before, but it's really worth a second look, especially given the stakes. In standard quantum mechanics, the fundamental building block of reality is the wave function. It describes the evolving probability distribution of all possible properties of the world or of tiny parts of the world. The results of your measurements are plucked from the wave function of whatever you're observing. We say that measurement collapses the wave function, obliterating all potential results in favor of one actual result. A wave function can span multiple distinct, even contradictory states. For example, an electron can be spinning in two different directions simultaneously. This is quantum superposition. And a wave function can also span multiple particles, holding information about the relationships between those particles. This is quantum entanglement. Let's say we have a pair of electrons, each in a superposition of spin states, say with spin axis simultaneously pointing up and down. But the electrons could also be entangled with each other, so that their spins are guaranteed to be opposite to each other, even if they aren't defined individually. Measurement of one electron would influence the other in a very real way, something Einstein referred to as spooky action at a distance. Standard quantum mechanics says that this is possible, but it leads to the seemingly absurd result of the EPR paradox. Let's see how it plays out. Bit direction is undefined. All we know is that they are opposite to each other. We give one electron to Alice and one to Bob, who then both go back to their separate labs to measure the spin. According to standard quantum mechanics, that spin is undefined until measurement. Upon measurement, it'll become fixed along the axis of the measurement device. Let's say Alice uses a vertical orientation. She'll measure the spin as being either up or down, with a 50-50 chance of each. Say she measures spin up, but that means we know what Bob's electron's spin must be. It must be down, even before he measures it. If Bob then chooses to measure using the same vertical orientation, he'll definitely measure spin down, but he could choose a different orientation. A horizontal measurement yields a 50-50 chance of being left or right for this down-pointing electron. But any other choice will actually be influenced by Alice's original choice of measuring orientation. When the scientists come back together to compare results, they'll notice a certain peculiar correlation between their choices of measurement axis and the other's measured spin. And it doesn't matter how far apart Alice and Bob's labs are across the campus or across the galaxy, the apparent influence should be instantaneous. This is the type of effect that made Einstein and company so uncomfortable. A foundational axiom of relativity is that no causal influence can travel faster than the speed of light. The EPR paradox was meant to show that this sort of undefinedness couldn't be the underlying reality because it violates the cosmic speed limit. He thought that each electron had to carry all of the information about its own physical state in a way that was somehow hidden from the wave function of standard quantum mechanics. We can imagine the same scenario in the case where the electrons do know their own spin all along. In that case, the spins are set at the beginning, still opposite to each other, but defined, even if Alice and Bob don't know what they are just yet. The scientists go off and make their own choices for their measurement directions, but now nothing that Alice can do will change Bob's results. When the two compare results, they will see correlations between the spin measurements because the original spin directions were correlated, but there's no correlation between one scientist's measurement results and the other scientist's choice of measurement direction. It wasn't until 1960, nearly 30 years after the EPR paradox paper was published, that physicist John Bell gave us a concrete test for all of this. He derived a mathematical statement, the Bell inequality, that is true in the case that the electron spins are set from the beginning and contained within the electron, but false if standard quantum mechanics is right and spin is undefined until observation. And it took another 20 years for the first Bell test to be successfully performed by Alain Aspect. That test thoroughly supported standard quantum mechanics. Countless Bell-type tests have been performed since, all with the same result. Apparently, entanglement is real, and it's as spooky as Einstein feared. But actually, the results of the Bell tests are not convincing evidence against realism itself. The world may still have a non-subjective existence. According to the Bell theorem, any local realist theory must obey the Bell inequality. So a violation of the inequality could be a violation of realism or of locality. Or, sure, of both. In a local realist theory, every point in space and time, every event, can only be influenced by a space-time event in its causal past, so near enough to have sent a signal. There are ways to save realism in quantum mechanics by crossing Einstein and abandoning this locality. Things like pilot wave theory and objective collapse models try to do that. On the other hand, the many worlds interpretation of quantum mechanics saves local realism at the cost of requiring multiple realities. If that price is too high for you, there may be another way, but I'm not sure you're going to like it any better. Let's play out the Bell test on something called a space-time diagram, with one dimension of space along the x-axis and time on the y. Alice and Bob start out together, acquire their entangled electrons, and then move sideways in space and up in time. Light travels at a 45-degree angle, and so if local realism holds, only events in what we call the past light cone of, say, Bob's location should have been able to influence whatever happens at his position. But quantum mechanics says that when Alice measures her electron, Bob's electron is instantly affected. That violates local realism. Now let's look at the case where the electrons start out with defined spins. It's no surprise that Alice and Bob observe opposite spins because we can see that both electron spins were determined by a single event in both of their past light cones. Alice and Bob may observe correlated information if there's a causal path to both of them. But here's where we find our loophole. The Bell test results are weird because Bob's measurements turn out to be inexplicably correlated with Alice's choices. That's only weird if Alice's choices themselves are independent events defined wholly in the present moment. Locality and realism would have been saved if it had turned out that the states of the electrons were fixed when their past light cones overlapped. But what if, instead, the future decisions of Alice and Bob are influenced within that same past overlap? Bell's theorem, his inequality is satisfied in local realist theories. But there is another condition to the validity of the theorem. That's the statistical independence of the measurements. It assumes that Alice and Bob can choose with absolute freedom, or that if they choose randomly, that their random number generator is perfect. But what if statistical independence is an idealization? Trace past light cones back far enough and everything is connected. What if those connections produce sufficient correlations between Alice and Bob's supposedly free decision for how they'll make their measurements and the states of the measured particles? It may still be possible to violate Bell's inequality without saying anything about local realism. This way out of the EPR paradox is called superdeterminism. Superdeterminism is, well, it's just determinism, the statement that the universe and any system therein evolves in a way that's uniquely predictable by the laws of physics and its initial state. Determinism on its own doesn't guarantee the sort of uncanny convergence in that evolution needed to solve the EPR paradox. That's what the super part is for. Some have argued that superdeterminism requires a kind of conspiracy of interactions to ensure that two messy meat computers make the right choices based on marginal interactions arbitrarily far in the past. Others, like Sabine Hossenfelder, argue that superdeterminism is actually the cleanest solution to the EPR paradox, and you can watch her video on that to decide for yourself. Regardless of its plausibility, superdeterminism is a loophole in the Bell theorem that physicists have tried to test. To close the loophole, a Bell test needs to be performed where the choice of measurement direction is truly statistically independent. And that's impossible, because if you trace the past light cone of any 2 points in the observable universe back far enough, they will overlap. Everything has a past causal connection with everything else. But we can at least do a Bell test where the deciders and the measurement subjects have past light cones that intersect with each other as far back in the past as possible. And so I'd like to introduce you to the cosmic Bell test. This was performed by Anton Zelinger's group at the University of Vienna in 2017. Their first effort used the light from a pair of distant stars as proxies for Alice and Bob. The random color of individual photons of that light was used in place of a random number generator to decide the measurement orientation in the Bell test. Now, this experiment used the polarization direction of photons rather than the spin direction of electrons, but it's the same deal. They observed violations in Bell's inequality with extremely high significance, which they claim ensures that no local realist influences could have messed with Alice and Bob's decision, except in the seemingly implausible scenario of the stars talking to each other and conspiring against us. The same team followed up with a cosmic Bell test using rather more distant objects, quasars several billion light years away, that pushed back any possible local realist influence more than half the age of the universe. Theorists are still debating how to interpret superdeterminism, although the majority seem to be on Anton Zelinger's side in dismissing it. Sabine is an emphatic voice on the opposing side. Let's stay neutral just for the moment and look at what we know. The many Bell tests, cosmic and regular, tell us that either locality or realism are wrong, or that there are multiple realities, or the universe evolves in unalterable lockstep determinism in a way that preserves correlations between measurement, subject, and measurer. The latter has philosophical implications for our own dreams of being detached observers independent of our subjects. But you know what? Quantum mechanics has been telling us that we are not that for 100 years. As for the question of free will, look, when philosophers come up with a reasonable definition of the thing, maybe we can talk. But think of it this way. Your mind has a physical substrate, your brain. Your mind isn't an illusion just because it's an emergent phenomenon. If your choices have a physical, even deterministic substrate, that doesn't change the fact that right now you know that you can choose whether or not to believe in a superdeterministic space-time. Hey, thanks for clicking that play button. Those views are actually really important for us. Now, if you think that this show is good enough to deserve even more than one click, you might consider trying out some of those other buttons down there. The like one is really good, and the subscribe button is amazing, certainly for us. Crazily, those buttons require exactly the same motor force from your finger as it took to watch this video. It's a great deal.
For businesses of all sizes, T-Mobile is reinventing business internet with super broadband.
Thank you to KiwiCo for supporting PBS. At 1/1000th of a second after the Big Bang, the Great Annihilation event should have wiped out all matter, leaving a universe of only radiation. We still don't know why any matter survived. Well, a new finding from the LHC brings us one step closer to understanding why there is something rather than nothing. Hey everyone, two quick announcements before we jump in. First, our With Great Power Comes Great Need for Storage and Distribution t-shirts and sweatshirts will be available until the end of the month on the merch store. Links in the description, web shooters not included. Second, as we mentioned last episode, we're starting a scientist live stream interview over on our Patreon. Each month, we'll bring on someone who's doing work that I consider amazing and important. Our first guest will be Dr. Matthew Kaplan, computational nuclear astrophysicist and longtime spacetime writer. Matt and I will discuss how real black holes feast on their surrounds and grow to such enormous sizes. One of Dr. Kaplan's papers on work we'll definitely discuss is in the link in the comments if you want to study up. The video will be made available to the whole Spacetime audience, but if you want to join us on the live stream, join us on Patreon at any level. There are more details coming soon over on the community tab, so hit the bell icon to get those notifications. The job of physics is to understand the behavior of matter and energy and space and time, to understand the how and why of stuff. But some would argue that the deeper philosophical question is why stuff even exists in the first place. Why is there something rather than nothing? It's been said that this is a question for philosophy, not for physics. But physicists who have a habit of thinking that no question is beyond their powers tend to disagree. Look, it's simple math, right? Nothing is zero anything. Something is any non-zero amount of any type of stuff. So if you start with nothing, you should be able to turn it into something by adding equal parts positive stuff and negative stuff. That's still technically zero stuff. Nothing and something can be mathematically equivalent. At least, that's a somewhat facetious interpretation of the argument that some physicists have given for why antimatter solves the something from nothing conundrum. Quantum fluctuations in an empty vacuum can produce matter and antimatter. This doesn't tell us where we got the vacuum or the laws of physics in the first place, but that's for another time. But antimatter does at least explain something about how a universe containing only bland, featureless potential can become one that's full of stuff. But there is another challenge to this nothing to something story. Matter and antimatter should destroy each other as soon as they form. Think of matter as the evil twin or bizarro world reflection of matter. Every particle of matter has an antimatter counterpart with precisely the same mass and precisely opposite in quantum properties like spin and electric charge. These quantum properties are strictly conserved. For example, positive electric charge can only appear from nothing if an equal negative electric charge also appears to balance the ledger. Like in Physics Girl's famous vortex-antivortex experiment, where twin whirlpools are created with a sweep of a dinner plate in a pool. It's like angular momentum, the spin of each vortex comes from nothing, but the vortices have opposite spin, so the total angular momentum remains zero. And if these vortices find each other again, they will cancel each other's rotation and vanish. So, antimatter is like the antivortex. It carries away the opposite twist in the otherwise twist-free quantum fields, allowing matter to exist. And we see the appearance of matter-antimatter pairs all the time. Raw radiation, like a photon, can spontaneously form matter-antimatter pairs, like an electron and a positron, in a process called pair production. It's like the photon is the plate dragging through the pool of the electron field. We think that the very early universe was one of pure and very intense radiation, and that all matter appeared in the form of matter-antimatter pairs. We also expect that these pairs would immediately annihilate each other. That means that after the universe cooled below the pair production temperature, all the stuff in the universe would quickly vanish away, leaving a light-filled universe that was empty of matter. That's clearly not the case. What actually seems to have happened is that all of the antimatter was annihilated, presumably taking with it an equal amount of matter, but for some unknown reason, there was just a little bit more matter than antimatter, 1 particle per billion to be precise-ish, and those lucky particular winners of the musical chairs of annihilation would go on to become the stars, the galaxies, and you. The minuscule asymmetry between the amount of matter versus antimatter at that early time is why there's something rather than nothing, or at least nothing interesting. It's a major outstanding problem in physics. According to the raw standard model of particle physics, matter and antimatter should behave exactly the same. That means if you replace every particle in the universe with its antimatter counterpart, then nothing would change. Positrons would orbit antinucleons, the anti-Earth would revolve around the anti-Sun, and anti-physicists wouldn't notice anything awry. The idea that the laws of physics are the same for matter and antimatter is called charge parity or CP symmetry. We can describe antimatter as regular matter that has had its quantum properties flipped. In particular, the precise antimatter counterpart of a matter particle has opposite charge, whether electric charge, color charge, or whatever, and opposite parity, which is equivalent to a mirror reflection, which notably flips its quantum spin. If the laws of physics are unchanged under this charge parity or CP inversion, then we say the universe is CP symmetric. But a CP symmetric universe would have no way to generate more matter than antimatter at the beginning of time. For that reason, CP symmetry must be violated in subtle ways, and we've actually observed that violation, first in the oscillation.
So, how do you want to do this?
Wanna
of the kaon, that's a particular type of two-quark particle, or meson. We've also seen it in a number of other mesons which contain the bottom, or beauty quark. When these unstable particles fall apart, they can leave behind a range of decay products, and the decay outcomes will have different probabilities that depend on whether it was the matter or antimatter version of the meson. But one thing that we've never seen until this new study is CP violation in baryons. These are 3-quark particles, like the familiar protons and neutrons, but also more exotic types. And if we want to understand the matter-antimatter asymmetry, we probably should understand it in the context of the type of matter that makes up all the visible stuff in the universe. So, without further ado, let's look at the new result from the Large Hadron Collider. The LHC at CERN in Switzerland is most famous for finding the Higgs boson back in 2011. As the largest particle collider in the world, the hope is that it can do a lot more, Many thought that the next great achievement would be to discover supersymmetry, and its so far failure to do so has confused and disappointed many physicists, but LHC is no one-trick pony. It supports many big experiments exploring big questions. And one of those is the LHC-B experiment. The B isn't for backup or plan B. The sole purpose of this experiment is to explore the subtle asymmetries between matter and antimatter through one little particle, the bottom quark, or the beauty quark, as LHCb prefers to call it. All of the familiar matter in the universe is rooted in the up and down quarks that make up protons and neutrons, along with their electron companions. But there are 6 quark types in total, including the top-bottom, strange, and charm quarks. Bottom/beauty are especially interesting because they are unusually susceptible to CP violation. Let me try to give you a quick overview of how this symmetry violation comes about. Quarks transform or decay via the strong and weak interactions. Quark color charge can change, and quark flavor or quark type can also change. These decays are often depicted with Feynman diagrams. Each diagram depicts a possible sequence of intermediate interactions that could lead from a given input to output state. We call each diagram a channel for that decay. But because quantum mechanics is mind-bendingly weird, the situation between our known states, the before and after the decay states, is fundamentally uncertain. To calculate the probability of going from a given input to output, you have to add together the probabilities of all possible intermediate states, because in a sense, all channels happen in a quantum superposition. A more familiar example of quantum superposition is the double-slit experiment. A particle travels through a pair of slits to a detector screen. It does so as a probability wave, and the final landing point of the particle is determined by how these waves interfere with each other after passing through the slits. It's more probable that the particle will land where the waves stack up via constructive interference, and less likely where they cancel in destructive interference. Well, something like this also applies to the alternate intermediate states in particle interactions. There's interference between the possible spatial paths within each channel, each Feynman diagram, but there's also interference between the different channels, a sort of crosstalk between the alternate realities of the different ways a quark can decay. This only makes a difference if there's an actual phase difference between the channels, just like the phase difference in the double-slit waves that can lead to cancellation. So the raw probabilities for each decay channel are identical for matter versus antimatter, but one thing that gets inverted in antimatter is the wave function phase that feeds into the decay probabilities. That leads to different interference profiles and so to different decay products. There are particular conditions required for this difference to be observable, but color and flavor transformations mediated by the weak interactions do the trick, and this is particularly strong in the decay of the bottom quark. For this reason, CP violation experiments have focused on particles containing these big quarks, and that means the LHC-B experiment that we're discussing today, but also Bell 2 at the Super KEKB accelerator in Japan, and the Barbar experiment at the Stanford Linear Accelerator. All have seen CP violating decays in B mesons, but just recently, LHCb managed to distinguish a significant difference in the decay of bottom quark containing baryons for the first time. LHCb studies these decays by taking the near light speed protons from the LHC ring and smashing them together in front of a series of detectors tuned to the expected energies of these decay products. They can pick out the bottom decays by sorting the many detections from each collision by the expected arrival time at the plates, and making use of the fact that these bottom-containing particles will have travelled a little from the original collision site before decaying. LHCb collected these decay products between 2011 and 2018, and spent the following years performing a careful analysis of the data that included sifting through the enormous number of particle detections to identify the products of a very particular event. They wanted to isolate the result of a B baryon or its antimatter counterpart breaking up into a proton or antiproton respectively, along with a kaon and a pair of pions. This would be their best chance to detect CP violation in baryons. And after all that particle sorting and number crunching, there was indeed a very real difference between the rates of this decay between the matter and antimatter B baryons. The asymmetry is only around 2.5%, but with a confidence of 5.2 sigma. That means CP violation is formally detected in baryons with only a 1 in several 100,000 chance of this occurring by random chance. And if B baryons do violate CP symmetry, it's not a stretch to think that this is probably true for baryons in general, including the protons and neutrons that make up the familiar matter of the universe. So, the stuff of the antiverse is subtly different to the stuff of our universe. So, have we explained why there's something rather than nothing? Not yet. Even with this observation, the degree of CP violation isn't enough to fully explain the amount of matter left over from the great annihilation event of the early universe. New sources of CP violation beyond the quarks are needed for that. There are high hopes that we'll find the necessary asymmetry in the leptons, so the electron and its sibling gluon and tau, and the neutrinos, Fermidant Nova and the upcoming June, as well as the Japanese T2K and the upcoming Hyper Kamiokande, hope to find lepton CP violation by observing how neutrinos oscillate between types. But if we don't find the needed degree of asymmetry in experiments like these, it may mean that we have to look beyond the standard model for new ways to explain the matter-antimatter balance. But one step at a time. For now, finding that matter and antimatter baryons are indeed gently different is a step towards understanding a much bigger question. Why does the universe have matter at all, rather than being a featureless, radiation-filled space-time?
You shop in the Acme app? You can count on prices that are the same online as they are in store. Even when you can't count on teenage appetites staying in the budget.
Discoveries like the one from the Large Hadron Collider are a reminder of how exciting science can be and how important it is to spark curiosity early on. That's why we're grateful to KiwiCo for supporting PBS. KiwiCo makes learning active with hands-on science and engineering. We'd like to thank Opera for supporting PBS, and you can learn more about them at the end of our episode. The James Webb Space Telescope has found galaxies that are too ancient-looking for the young universe in which they were found. Now, you may have heard that, but JWST keeps finding them, and our recent efforts to solve this conundrum point in wildly different directions. Have we found galaxies older than the universe itself, or did we just learn something incredible about how galaxies form? Before we get started, a couple of quick announcements. First, we have some new data. Liking and commenting really does help get the episodes shared. So, please do both of those things. And we've also learned that the number one reason that people support us on Patreon isn't actually the perks. It's simply to support the Spacetime community and the work that we do. So, for those of you who do support, thank you so much. But don't get me wrong, there are perks, and they're good. There's a link in the description if you'd like to join. This really would be a huge help. Next up, Today's episode is part of PBS Earth Month. PBS is celebrating by releasing a ton of great new episodes diving deep into our amazing planet. In particular, you might enjoy the latest episode of Be Smart, which explores the math, science, and history of the Mercator map, a flawed work of genius that, in more ways than one, changed the world. Links to that episode and the full Earth Month playlist also in the description. Next up, we're excited to announce our third celebration of a galaxy far, far away with our return of the geodesic merch. Because whether you're following a geodesic on a closed universe or reliving your favourite saga, you'll always know where you'll end up. And now until May the 4th, there's 10% off the whole merch store, with special deals if you combine your order with previous May the 4th merch. Now, onto the episode. Telescopes are time machines. Light takes time to reach us, so we see distant objects as they were when their light began its earthward journey. As our telescopes become more powerful, they see further, and so more and more of the past becomes accessible to us. The James Webb Space Telescope is one of the most powerful time machines ever built. It's powerful enough that it's discovered galaxies whose light has been travelling to us since the universe was just a little over 2% of its current age. The universe back then should look different, right? Those galaxies should look different. After all, this is when galaxies first started to grow, when they should have been vigorously forming many of their stars. They should look like hyperactive kids. Those types of galaxies probably are around back then, yet JWST has also seen much more developed adult galaxies, some of which look way too big and way too ancient looking for a universe that's only a few 100 million years old. Over the past year or two, this mystery has made the pop sci rounds. That included some breathless speculation like the idea that the entire Big Bang model is wrong. If there are ancient galaxies 13 or so billion years ago, then how can the universe only be 13.5 billion years old? So far, we have not weighed in on this conundrum. Now, many others have done a fantastic job laying it out and debunking some of the foolishness. Dr. Becky in particular was on top of the progress as new data came in from JWST. So why should we cover it now? Well, first, a lot of you have asked for our take, and it's time to go on the record. Second, the evolution of this mystery has been quite an emotional roller coaster, swinging from unsolvable to solved. And now there's new work that swings back in the direction of WTF. So let's talk about the current status of the early galaxy conundrum. And before that, let's talk a bit more about what we actually expect the early universe galaxies to look like. Galaxies pull themselves together from tiny density fluctuations in the very early universe that we see as the dappling of the cosmic microwave background. The CMB reveals regions with tiny excesses of matter, hydrogen gas, but more importantly, dark matter, which outweighs the gas by a factor of at least 5. As dark matter pulled itself together by gravity, it pulled the gas in with it. And as that gas compacted, the first stars were also born. These very early galaxies must have started small, but with pretty crazy star formation due to the enormous abundance of gas at that time. As those galaxies continued to grow, they collided and merged and eventually built themselves into the mature galaxies that we see today. We think we understand this stuff pretty well, or at least we thought we did. Between the precise CMB measurements and our theoretical understanding of gravity, star formation, etc., our computer simulations allow us to explore the possible growth scenarios for galaxies. We can predict, for example, that early galaxies should have been forming stars like crazy due to the enormous amount of raw material, the hydrogen gas, around back then. One thing that should be even more robust as a prediction is the size of dark matter halos. These are the giant pools of dark matter that encompass all galaxies and hold them together. Because dark matter should not be strongly affected by the complicated behavior of the gas in the stars, we have high confidence in our understanding of how those halos grew over time. Or at least we thought we did. One very clear prediction of this whole model is that a lot of this halo growth should have happened in the first 10% of the universe's age. In that first 1.5 billion years since the Big Bang, there should have been essentially no very large halos, and so no very large galaxies. And that's what the theory and the simulations say. But to check these, we need powerful time machines, telescopes. Now, as our telescopes got bigger and our cameras got more sensitive, we were finally able to probe early enough times to properly test our models of halo growth. And this is where the problem started. Around 15, 16 years ago, when our high redshift galaxy surveys, aka really far away galaxy surveys, finally reached these distances, we got some answers. And those surveys started seeing a few cases of what looked like giant halos at earlier and earlier times, and also the hint of overly red galaxies in the early universe. Galaxies that are actively forming new stars should be bright at short wavelengths because they have lots of giant, hot, short-lived stars. They are relatively blue in color compared to older galaxies, and older galaxies that are no longer so actively forming stars should look redder because the short-lived blue stars have exploded already. Those earlier surveys didn't reveal anything crazy yet, just a handful of cases where galaxies looked too big and or too evolved compared to what was expected from our models. In 2018, Charles Steinhardt and team articulated this emerging tension in their paper, The Impossibly Early Galaxy Problem. But impossible things are impossible. It's right there in the name. So several not impossible explanations for these galaxies were devised. For one, we don't really see overly large dark matter halos directly. We only see the starlight, and then we use that starlight to infer the mass of the stars and then the mass of the halos that contain them. But that step requires assumptions, and if any of the assumptions are wrong, then perhaps we got the wrong halo mass. And the redness of the galaxies that suggests an old stellar population could be due to other things. And there are several other issues with these inferences besides, and I'll come back to possible solutions in a bit. But even if the galaxies that were found in these ground-based surveys were really too old-looking and too big-looking, well, we haven't quite broken all of astrophysics and cosmology yet. If we strain our models of galaxy formation, then we can potentially speed up galaxy evolution to show why these things exist by the time that the universe is 10% of its current age. What we'd really like to do is to look back even further in time to see if we can find the time when these galaxies were themselves growing. And that's what we did with the James Webb Space Telescope. JWST was designed to push this early galaxy game to new extreme limits. It's the largest telescope ever deployed in space, which means the most powerful. It's also designed to be sensitive to very long wavelengths of light, deep into the infrared part of the electromagnetic spectrum, the mid-infrared as we like to call it. That's important for these first galaxies because of the expansion of the universe. Their light has been travelling to us for much of the age of the universe. Because these EM waves are travelling through an expanding universe, they get stretched out, their wavelengths lengthened. This is cosmological redshift, and higher redshift means longer travel time and greater distance. For galaxies that we're interested in, this redshift converts visible and even ultraviolet light into mid-infrared, which is why JWST is needed. The first efforts with JWST used similar methods to our ground-based galaxy surveys. So maybe I give you a bit more detail on that. Now, the first thing that you do in a galaxy survey is to take some pics with different filters corresponding to different wavelength bands, and then you compare the amount of light in each filter. We call this photometric imaging. We can learn a lot of stuff from the ratios of filter brightnesses, the so-called colors. We discover candidate galaxies this way. We make a crude estimate of the distance because the color ratios suggest a redshift. We then constrain the stellar population, both the number of stars and the distribution of different types of stars. For example, the redder colours mean an older population with few massive stars. So what did JWST find? Well, first it confirmed the presence of overly massive and overly old-looking galaxies from the earlier studies. And remember, that was from a cosmic age of around 10%, which is a redshift of around 4. Now, a critical advantage of JWST is that it's sensitive enough to do proper spectroscopy on these galaxies. It can measure their spectrum, the amount of light as a function of wavelength. These spectra confirmed that the redshift are indeed very high. They also confirmed that the redness of the spectra is due to highly evolved stellar populations rather than, say, there being a lot of dust in these galaxies, which can cause a similar reddening in photometric analyses. With these confirmations of old-looking early galaxies, researchers more broadly really started to pay attention. The media started to pick up on this when JWST pushed to greater distances at earlier times and kept finding these things. Currently, the earliest candidate giant evolved galaxy discovered by JWST is at redshift of 7.3 at just 5% of the universe's age. Now it seems we have a real conflict with our models of galaxy formation. Dark matter halos too large and stellar populations too evolved for the short amount of time that they've had to develop. And this is why we started to hear some hysterical claims that the universe is twice as old as we thought, or that the Big Bang model is completely overturned. It's not, and it isn't. There's just so much independent corroboration of our model of an expanding 13-point-something billion-year-old universe. You can't point to one admittedly intriguing discrepancy and decide to throw the baby universe out with the bathwater. There are much more parsimonious explanations for our improbably early galaxies. Let's look at one of the most compelling. Remember that when we calculated the masses of these supposedly gigantic dark matter halos, we based them on the starlight that we see, and that requires an understanding of the relationship between these two things, the starlight and the dark matter halo mass, and that involves assumptions. Here's how that works. One assumption is that the halo mass is connected to the mass in stars, and that stellar mass is connected to the amount of light that we see in those stars. But we don't see the light from all of those stars. Typically, the light we collect is dominated by the brightest stars in the galaxy. We then have to decide on the relative numbers of different types of stars so we can extrapolate from the observed starlight to the mass of the stars, seen and unseen.
Liberty Mutual helps you.
Einstein, along with Oscar Morgenstern, insisted on accompanying to his interview in the hope of stopping him from blurting out his proof, which he very nearly did anyway. Oh, and speaking of Einstein, once, as a birthday present, Gödel gave Einstein a time machine universe, a solution to Einstein's equations that proved that even general relativity is broken. We've got a couple of quick announcements before we start. First, our eternal battle against the algorithm continues. The best way to encourage YouTube to share our videos is to like and comment. Doing both really makes a difference. And if you're new here, subscribe, hit the bell, and introduce yourself in the comments. We're friendly. Next up, we're excited to launch our Universe in a Black Hole t-shirt and hoodie. If you believe we're trapped inside a black hole, where space and time swapped roles and the Big Bang was just the other side of a collapse, then this is the shirt for you. We're also still offering up our Black Hole Light Curves desktop and gaming mat that shows the ways light is warped by the gravity of a black hole. Plus, our UV glow Kerr rotating black hole designs and dark energy mugs are all still available. Links in the description. Now, onto the episode. It's not an exaggeration to say that Gödel and Einstein were best friends. The aging Einstein once said that the only reason he continued to show up at Princeton was for his walks with Gödel. And so, when the occasion of Einstein's 70th birthday approached, it's no surprise that Gödel enthusiastically agreed to contribute to a book of tributes to Einstein's work. At first, Gödel thought to write a reflection on the relationship between Einsteinian spacetime and the ideas of the philosopher Immanuel Kant. As was his wont, Gödel fell down a rabbit hole, and in the process of writing this one essay, he came to understand general relativity as well as anyone in the world. And then he stumbled on something deeply worrying, an inconsistency at the core of his best friend's theory. The rabbit hole deepened. The deadline for the essay came and went, but so important was Gödel's contribution that the book had to wait. When he was finally done, the reason for the obsession became clear. Gödel had found a solution to the Einstein equation, the core of general relativity, that proves that Einstein's theory by itself does not guarantee a clean chain of cause and effect like it was supposed to. He built a space-time metric, a universe, where every point in space and time there exist return loops that can bring you back to the location before you left. Now, by the time of Gödel's discovery, we already knew of solutions to the Einstein equation that allow time travel, but all of them require something that can be argued is impossible: negative energy density. So just add a prohibition of this impossible stuff, and the broken solutions go away. This prohibition is called the weak energy condition. With the Einstein equation plus the weak energy condition, a deterministic universe with unambiguous causal ordering seemed guaranteed. That is, until Gödel. He found a new way to time travel and to break causal structure with no impossible ingredients required. And the result is the Gödel universe, where time travel isn't just possible, it's inevitable. So let's take a trip into the Gödel universe. First, by time traveling back to Relativity 101. In relativity theory, space and time are not clearly separated. They're both part of a four-dimensional object called spacetime. Depending on motion and gravity, space and time become mixed, trading into each other. The classic way to depict this is with a space-time diagram, with just one dimension of space. Everything moves up through time, but if you're also moving through space, you move on a sloped line. Shallower is faster, and 45 degrees represents the speed of light. Because nothing can travel faster than light, you can only ever influence parts of the future in this cone, your future light cone. Meanwhile, your past light cone represents the parts of the past that could have had an influence on you. No possible signal could connect you to the regions that are outside these cones. So you can travel, or can have travelled, any path within these cones. We call these time-like paths because on these, your motion up through time is greater than your motion sideways through space. Paths into the forbidden zones are called space-like. more space than time is traversed in these, and that supposedly is impossible. But let's try anyway. Say we jump in our rocket ship and accelerate away from the Earth, quickly reaching a large fraction of light speed. Relativity tells us that my time axis shifts relative to the direction of axis back on Earth. From Earth's perspective, my time and space coordinates get mixed. My clock slows, my length contracts. If I actually reach the speed of light, my clock stops. And if I could go faster, well, from the perspective of at least some observers, my clock actually reverses and I appear to move backwards in time. This is equivalent to breaking free of your light cone. Once you can do that, the past is accessible to you. And a long time ago, we did some episodes that showed exactly how this works. The impossibility of superluminal motion is directly connected to the impossibility of time travel in special relativity. Both are baked in via the Lorentz transformation. This is absolute protection of the causal structure of space-time in the absence of gravity. Gravity changes things because it bends the path of light, so it can tip our future light cone. For example, approaching the black hole, light paths are bent by the black hole's gravity, and so our light cone bends towards the event horizon, while our entire accessible future ends up lying inside the black hole. And below the event horizon, the light cone tips fully sideways, which means the down direction becomes our new time coordinate. Now, if you could turn around and keep your light cone aligned like this, you really could travel back in time. But in a black hole, you can't turn around. Your future is only down. Well, let me actually revise that. In a rotating black hole, a Kerr black hole, there is a region deep within where angular motion becomes time-like. Space is spinning so quickly that a circular path gets you back to where you started at the same time that you left. We call this a closed time-like curve, a CTC. It's time-like in this case because you never violate relativity by leaving your forward light cone. These regions of the Kerr black hole may not even really exist, and in any case, it's a pretty useless sort of time travel because you're stuck behind the event horizon anyway. We can force closed time-like curves into the accessible parts of the universe by bending space-time in various exotic ways, wormholes, warp drives, etc. But in all cases, these require some sort of negative energy. But then came Gödel, of course. Even before Roy Kerr came up with the rotating black hole solution, Gödel realized that rotational motion was the key to time travel. The general effect he relies on is called frame dragging, the twisting of space-time due to a rotating mass. And we've actually measured this. Gravity Probe B sent a gyroscope in orbit around the Earth. Now, a gyroscope is supposed to always point in the same direction. In fact, Gödel calls the device a inertial compass in his paper. But the gyroscope in Gravity Probe B slowly swiveled from its original pointing as it orbited due to both the gravitational curvature, but also due to the twisted space-time, the frame dragging caused by Earth's rotation. This angular shift is also accompanied by a shift in time. But in the case of Earth's frame dragging, that is a far too weak an effect to be measured. But in principle, if you travel around the Earth the right way, your clock slows due to the angular motion. It's never enough to freeze time altogether, though. Even around a rapidly rotating black hole, there are no closed time-like curves on the outside of the black hole, only deep within. But Gödel realized that this frame-dragging effect could still break causality if it happens in a space-time where the effect can add up. Now, the key is to describe a space-time which has a fundamental twist to it everywhere. All points feel frame dragging, not just around single spinning objects. We say then that it has global vorticity. All space-time points rotate relative to neighbours, not like every spot is spinning, but rather like there's a vortex of world lines in an infinite 4D space-time that has no centre. There are other requirements. A negative curvature or hyperbolic geometry is needed to allow this centerless rotation, and a balance of smooth positive matter and negative dark energy are needed to keep this universe static in size. But tuned right, Gödel showed that such a universe can be full of closed time-like curves. Let's see what this looks like. This saddle shape is a representation of a two-dimensional hyperbolic space. We're reserving the z direction for time so that we can stack these planes to represent a 4D universe. Zooming in, it looks flat locally, but the negative curvature is still there. Now, you don't notice anything weird moving through this space, even though the underlying twist is there. You notice this when time moves forward and neighboring particles start to follow twisted paths. From any point in this space, as you travel outwards, your light cone tilts relative to the reference frame of your starting point. And beyond a certain distance, the Gödel horizon, it has tilted far enough to allow travel back into the past, or at least to claw back some of the time you spent traveling. But with a carefully planned route, traveling in a loop, you can steer your future light cone to eventually contain your starting point. Another way to think about this is that by mixing time with the angular coordinate, your motion in a loop can take the place of your motion through time and can even reverse temporal motion. That's right, Gödel invented the time turner. Turn enough and you travel backwards in time. But with restrictions. You have to travel out beyond the Gödel horizon from your starting point, which means you can't just spin on the spot and move into the past. The time-traveling possibilities of the Gödel universe are fun, but they aren't the real point. The real point is that this solution to the Einstein equation is a counterexample to the idea that baseline general relativity, the Einstein equation, plus the weak energy condition are enough to ensure sensible universes. Before this, any valid GR spacetime could be sliced into layers of consecutive nows where the exact configuration of everything, the particles, the fields of each of those slices, can be used to generate the next slice. This perfect global determinism isn't true in Gödel's universe, and the past and future become tangled and not clearly definable. Gödel proved that general relativity doesn't guarantee spacetimes that have a rigid causal ordering. At least in some cases, like in Gödel's universe, we can't say whether A caused B or whether B caused A.
For businesses of all sizes, T-Mobile is reinventing.
Supporting PBS. Some people worried that the Large Hadron Collider would smash particles together so hard it would make black holes that would swallow the Earth, open wormholes to other dimensions, etc. It didn't, and it won't. But the LHC may be making a very different kind of portal. A portal to the dark sector. This isn't another name for the Upside Down. Rather, it's a hypothetical family of elementary particles that exists in parallel to the familiar particles of the Standard Model, but are invisible to the Standard Model, invisible to us, and therefore could be the answer to the dark matter conundrum. And what is this portal? Well, it's the particle that the LHC was built to find in the first place, the Higgs boson. We've got a couple of quick announcements before we start. First, our eternal battle against the algorithm continues. The best way to encourage YouTube to share our videos is to like and comment. Doing both really makes a difference. And if you're new here, subscribe, hit the bell, and introduce yourself in the comments. We're friendly. Next up, we're excited to launch our Composition of the Universe nickel and enamel pin, now with a holofoil backing. If you want to flex your knowledge of dark energy, dark matter, and the terrifyingly small slice of ordinary matter that you and our world is made of, check out our first pin of 2026. And if you prefer your mornings fueled by dark energy, we've also got a brand new dark energy mug. Plus, our UV Glow Kerr rotating black hole hoodies and shirts are still available. Links in the description. Now, onto the episode. The Higgs boson was discovered with the Large Hadron Collider back in 2012. Physicists celebrated, a few collected their Nobel Prize, and they got back to work. They amped up the collider with the expectation of discovering the particles that would lead us to the next level of physics. For example, supersymmetric particles that would simultaneously explain the Higgs mass, give us candidates for a dark matter particle, and even bolster string theory. No such particles appeared. Okay, so maybe the undiscovered particles are just so massive that there wasn't enough energy yet to grant them that mass. E equals mc squared, so not enough E for the needed m. So we kept juicing up the collider and kept finding nothing. At this point, the LHC is near its maximum planned energy, 6.8 tera electron volts in the most recent run, and the design goal is 7 TeV, so it's unlikely that new particles will appear before it maxes out. Disappointing? Maybe. But was it worth building the LHC just to produce the Higgs? Absolutely. Besides completing the standard model, it could well be that the Higgs boson itself is the key to the physics that lies beyond, and that physics may finally explain dark matter. Now, searchers for dark matter have typically focused on finding a dark matter particle, as though a single add-on to the standard model could solve the problem. One of the best such candidates was the sterile neutrino, which Fermilab recently put to bed as the simplest way out of the problem, as we recently discussed. Now, this might still work, but it's getting dodgy. Or it could be that one of those undiscovered high-mass particles, like those predicted by supersymmetry, are dark matter, but again, the LHC almost certainly won't find those. In general, the parameter space for dark matter as a single particle is getting worryingly narrow. But, just maybe, the problem is that dark matter isn't just a single particle. Maybe there's an entire family of particles that exist in parallel to the standard model that are all invisible to us. And by us, I mean us standard model creatures. How would that even work? In order to do the job of dark matter, the candidate particle needs to be very difficult or impossible to detect via interactions with the standard model forces, electromagnetism and the weak and strong nuclear forces. Their coupling to these forces needs to be weak or non-existent, leaving only gravity as the force linking those dark particles to the standard model. In order to be invisible to the standard model, dark matter cannot possess any of the standard model charges. So no electric charge, no color charge, no weak charge. We can imagine single particles like this, but we can also imagine an entire family of particles with no coupling to the standard model. Such a family is called a dark sector, and its stable particles would be good dark matter candidates. Now, just because a dark sector doesn't hold standard model charges, it may still have its own charges and its own internal interactions. It could even look a lot like the standard model. So maybe we'd have dark quarks, dark leptons, dark bosons that could interact to give dark protons, even dark atoms. Or its interactions might be very different to the standard model. Based on how dark matter appears to be distributed in our universe, our hypothetical dark sector probably isn't forming the same cool structures as the standard model matter. So there probably aren't any dark sector planets or dark sector aliens in the room with you right now. Probably. So what's the use of a dark sector? Well, its particles could be light enough to already be within the energy range of the LHC. Because they're dark, the LHC detectors won't spot them directly, but that doesn't mean we can't notice their influence. Let's look at what happens then when two protons collide in the LHC. You can think of protons as tight bundles of several quantum fields, like knots in which each thread has its own internal weave. Collisions momentarily loosen these knots. They can then retie themselves in different forms. But not just any forms. Parts of the knot are undone or retied only in pairs, and the weave of the threads, the symmetries of the fields, persist in the retying, in the final particles. That means that conservation laws must be obeyed, energy and momentum and various charges, and also internal symmetries must be respected. A dark sector's symmetries can look like those of the standard model, but they come from different gauge fields, different weaves to its threads, and that results in different types of charge that don't talk to the forces of the standard model. So obliterated protons don't produce the fabric needed to make such particles. Not directly, anyway, but there is a way. If some of the debris of the proton collision can settle down into the simplest possible field configuration in the standard model, one lacking the complex symmetries, then that particle could then go on to decay into dark sector particles. Now, the least knotted part of the quantum field weave can be retied into anything respecting its simplest symmetries. More technically, only uncharged standard model field configurations, so-called singlets, can couple to the dark sector quantum fields. We call these dark sector portals, and these field configurations are the only way to move energy between the standard model and the dark sector. There are very few such portals. Examples include photon-dark photon mixing, the hypothetical sterile neutrino and axion couplings, and the Higgs field interactions. The Higgs may be the most promising of this group. Knowing that the Higgs exists and knowing how to make it is certainly important, but the Higgs is arguably the cleanest dark sector portal. The Higgs field is a scalar field, the simplest possible quantum field. Besides being less knotted by complicated symmetries, scalar fields are also uniquely good at coupling with other fields. That's why the Higgs couples so widely to grant particles their masses. So the expectation is that the Higgs would also be great at coupling with other sectors, including dark ones. Thank you to Brilliant for supporting PBS. Some things really do seem to be impossible, like faster-than-light communication, or breaking the second law of thermodynamics, or learning the second law and not being forever haunted by the whisper of the heat death. The universe seems to conspire to thwart any attempt to do certain things. And for a while, it seemed like the quantum structure of space-time might be part of this forbidden knowledge. But now, research has found ways to trick the universe into revealing its quantum underbelly. We've got a couple of quick announcements before we start. First, our eternal battle against the algorithm continues. The best way to encourage YouTube to share our videos is to like and comment. Doing both really makes a difference. And if you're new here, subscribe, hit the bell, and introduce yourself in the comments. We're friendly. Next up, we're excited to launch our Composition of the Universe nickel and enamel pin, now with a holofoil backing. If you want to flex your knowledge of dark energy, dark matter, and the terrifyingly small slice of ordinary matter that you and our world is made of, check out our first pin of 2026.
So that's a 12 on the dice, plus 8 for my short bow. That's a dirty 20, plus 4 from Adam. Guidance, thank you very much. That's a 24, that'll definitely hit. Then I'm using my short bows, so that's 1d6 plus 4, 4 plus 4 is 8. I was just hidden behind that tree, so I have sneak attack, which is 5d6. 6 plus 5 plus 4 plus 3 plus 6, that's 32 damage.
Alright.
God damn it. She's quick.
Holy shit. Alright, so the arrow strikes him in the chest. The orc convulses and goes down to the ground, killing him instantly. Rowan, you're up. What do you want to do?
You've taken out the tiny little one, so I think I'll take out the big boy.
Alright, I mean, just to remind you, your current health is...
I think I know what my health is, so...
Alright, sure. Make an attack roll.
Okay, here we go. So I've got 4, 2, and then... What's that? Yep, there it is.
That's a 9. You rolled a 9 on the dice. What's your modifier?
The modifier, yeah, because 9 plus 4, and then 4 is that?
I didn't say anything.
If you've already figured it out, I don't mind if you want to say it, you can say it.
I'm not doing the maths for you, Rowan.
I don't want you to do the math for me. I can do the math myself.
Go on.
1, 7, plus the multiplier that I got, and then the thing that I had over there.
Oh no, I get that too.
Last, I sang the song, which gave me a damage buff. Yeah, and then that gives me a grand total of 172.
172? Whoa, that's so much!
Oh, Adam, that's not right.
No.
That's not right.
You're going to lock in 172 as your answer.
Yeah.
From a 9 on the dice.
Yeah, does that hit?
Let me check. It just misses. Yeah, 173 armor plus. Crazy.
Damn it.
Well, your attack whiffs. Oh, yeah. And then unfortunately, it's now the orc's turn. And as I tried to warn you, you have 3 hit points currently. He gets... yeah, that's going to hit. So he's going to hit you for 12 points of damage.
Oh. Oh no, am I okay?
You had 3 hit points and he did 12 points of damage.
Am I okay?
3 minus 12, Rowan. Is that less than 0?
Am I okay?
Which one's bigger, 12 or 3? No, you're not okay. Go down to your knees, you're dying. You guys finally arrive at the Bald Raccoon Tavern. The air is musty and it smells a little bit like spilled ale and damp timber. What do you do?
Right. What are we doing here again?
The Tacit Scroll states that we'd find the dread wizard Gibraltar in the tavern.
Yes, and he shall have the fabled grimoire of restitution upon him.
Yes, we should find that.
Okay, sweet. I look around the tavern.
Excellent. So, you examine your surroundings. Your eyes are drawn to the far corner, where you see a mysterious figure, singularly illuminated by a lone beam of moonlight. He is shrouded in a heavy purple cloak, and a large dusty tome sits on the table in front of him.
Okay. Is there anyone else in this tavern?
Yes, there are a few patrons and, let's say, a waitress.
Okay. This waitress, what does she look like?
A human woman, average age, carrying a tray of drinks.
Are you there, waitress? What's your name?
Oh, my name. Oh, yeah, it's an easy one. It's Schmurple.
Schmurple. What an unusual name. Where's it from?
Around. Excuse me, I should.
And how long have you worked in this tavern, Schmurple?
Just a long, long time. Yeah. But in all my time working here, I've never seen anyone quite as mysterious as that guy over there. I wonder what that's all about.
Mysterious man. That's cute. Schmurple, how many siblings do you have?
I've no siblings, only child. Yeah.
Do you have any family at all?
No.
What, no family at all, not even parents?
No, well, I've got parents, obviously.
Well, what are their names?
Jeremy and Meredith.
Oh,
What an interesting contrast to Schmurple.
indeed.
Now, what are your
most vivid childhood memories and your most character-defining moments from your adolescence?
I can't quite recall. So you have amnesia? Well, that's mysterious.
Could be the dread Wizard of Bronze or not even know it.
Yes, I'm finding your inability to give us straight answers about the intimate and specific details of your life very mysterious.
Mysterious? No, look, I am just an ordinary waiter. Nothing interesting or mysterious here. Not like that guy over there. Look at him. He's like swimming with mysteries. Look, I bet he's got a great, like, fully fleshed out backstory. Not like boring old Slurple here.
I thought your name was Schmerple.
Suddenly, at that moment, the robed man stabs her in the back.
Oh no! I'm dying! I have been murdered by this mysterious robed man. I wonder what his deal could be.
Before you can jump in and save them, Slurple dies on the ground. Schmerple, whatever. Before you can save her, the robed man stands over her body with a bloody knife in one hand and a grimoire in the other.
Ah, adventurers, you have arrived.
I see. Very tricky. I cast Speak with the Dead on Schmerple's fort.
Alright, you guys arrive at a dusty old tavern. It's practically empty except for a few drunk patrons dotted around. Sit down at a table. What do you want to do?
Sorry, Rob, before you start, I have a quick question for everyone. In this campaign so far, have any of you pooed?
I mean, of course. I've pooed, right?
Yeah, but have you said in character in the campaign that you've pooed?
Adam, gross.
Well, it's just a bodily function, Alan.
Well, obviously, we will have pooped quite recently, I imagine.
Yeah, but have you specifically said that you're pooping at the table?
No, but we're definitely pooping, right, Rob?
Well, I mean, you haven't specifically said you're pooing.
So you're saying that none of us have pooed?
No.
That means that we haven't pooed in months. That seems like a massive oversight, Rob.
Yeah. Rob, why are we pooping?
Well, you haven't asked to poop. Shall we just get back on with the campaign?
No, actually, I want to hear this. Can you just let it happen?
I want to poop.
You can if you want.
Okay, is there a toilet in the tavern?
There probably would be, yes. Yes, there is.
I poop?
What, at the table?
No, I go to the toilet and I poop.
This is great fantasy roleplay, guys. I'm having a lot of fun.
Actually, start.
Okay. Make me a constitution check and walk me through how the poop goes.
Okay, I get up on the table and I go up the stairs. I do then. I locate the bathroom. I go outside the toilet. I take my pants off, sit down on the toilet, and I poop. Oh.
What did you get?
What happens?
I guess it's not a very enjoyable poop. Been clogged up inside you for months. And through the effort of pushing it out, you take 3 points of bludgeoning damage. Oh, and what's more, you took a point of exhaustion from the strain.
YouTube Premium is ad-free YouTube and the YouTube Music app all together. One subscription.
How was I supposed to know that speak with plants wouldn't work on the guard?
Because he's no, I can't even. I can't even.
Guys, there are two viable options, right? The first one is either we go back to the Rangers Guild or we find a way to scale this wall. Do you have any ideas?
Anyone got any rope or anything? Nope.
Oh, did you prepare fly today? We could levitate over.
No, I swapped it out this morning for animal friendship.
Surely there's a way to get over it. The wall isn't even that tall. Okay, do we pick up any tools or supplies that can help us?
No, man.
I guess we're walking back to the Rangers Guild.
Or maybe Rowan has ideas first.
Nah, sorry, man. I got nothing.
Nothing?
Nah.
You didn't pick up anything from the Carpenters Guild when you were looting that?
I think so. Oh, I did get one thing.
Yes.
Is that useful?
I don't think so, no.
Worth a shot.
Was it? Was it worth a shot, Ryan?
Oh, I'm sorry, Ben. Unless you're trying to problem solve it.
Okay, seriously? So none of us have anything to help us get over this wall?
I only loot gems.
That's not helpful. Maybe you just double check your inventory, Rowan?
Okay, nah, nothing.
Oh, while you're checking your inventory, you noticed something. Make me an investigation check.
Okay. 3.
Nah, actually, you don't notice anything.
Hang on. Why are you getting me to do an investigation check? Like, is there something around here that we're not noticing or something? Like, actually, can I do, a perception check?
You absolutely can, yes. Roll a perception check.
Okay. Hiya.
Lumbering cave with Liberty Bibbity.
Welcome to Mojo Plays, and today we're looking at the first entry of one of the busiest series of all time to see if there's anything we missed in arguably the simplest entry. These are 20 things you didn't know about Kingdom Hearts 1. Let's go. Before we continue, we publish content all week long, so be sure to subscribe and ring the bell to get notified of our latest videos. The greatest story of all time.
I remember making the double jump.
Some of the biggest gaming ideas come from years of planning and endless meetings. Then there's Kingdom Hearts, which apparently owes its existence to two people sharing an elevator. For a series that combines Disney cartoons with the usually more serious worlds of Square Enix, you'd expect a mountain of paperwork to be involved. Surprisingly, that wasn't the case. During Disney's D23 event in 2017, director Tetsuya Nomura explained that Square executive Shinji Hashimoto and a Disney executive regularly bumped into each other because both companies were located in the same Tokyo building. Casual chats eventually turned into discussions about working together. Before anyone drafted a grand proposal, the idea had already started. Imagine writing fanfic with your elevator homie and it becomes one of the most profitable series of all time. TP. Few things get gamers digging through old files faster than the discovery of unused content. In 2016, a YouTuber poking around the data of Kingdom Hearts stumbled across something unusual, an unfinished 3D model of a ship hidden within the game's code. There was no textures or characters or events attached to it, making it look like a world that never made it past the planning stage. What caught people's attention was the label attached to the area. Other locations in the game used short abbreviations, such as Hollow Bastion being listed as HB, while this mysterious map was tagged TP. That immediately sparked speculation that it may have been connected to Disney's Treasure Planet. Whether it was cancelled content or an early tease, fans still love theorizing about it today. Plot blowhole.
Yeah? With this, we can get out of here, Father.
Really? With this blue lock, you think so?
Sometimes the biggest mysteries in a game aren't hidden bosses or secret endings. They're little details that make you stop and think, hang on, that doesn't seem right. Players noticed one of these odd moments in Kingdom Hearts involving Pinocchio. The story treats Monstro as the place where Sora, Donald, and Goofy first meet the wooden troublemaker. Yet, if you visit Sid's shop in Traverse Town after unlocking Agrabah, Pinocchio can already be found hanging out around there. That creates a pretty strange situation. If his official introduction hasn't happened yet, how did he manage to show up in another world beforehand? The simple answer is that you are supposed to see Pinocchio first in Traverse Town and then in Monstro. Unfortunately, most players didn't play the game in that order, creating forums upon forums of gamers asking, how does Sora know Pinocchio?
It's me.
Scrapped Riku fight. Video game developers are constantly moving things around during production, and sometimes those abandoned ideas end up just as interesting as the final version. One example from Kingdom Hearts involves the showdown between Sora and Riku. Most players know this battle takes place in Hollow Bastion, but that apparently wasn't always the plan. Early development pointed towards a darker version of Destiny Islands as the arena, an area referred to as Crumbling Islands. This location still exists in the game's data, and players using devices like a Game Shark have been able to access it and fight Riku there instead. It's a fascinating glimpse into an alternate version of the game.
Always knocking like the speakers.
YouTuber, the gamer's joint, accidentally stumbled across a hidden area in deep jungle that many fans had never seen before. By making a very specific turn while sliding along the vines, he was led to a secret minigame centered around collecting fruit alongside Tarzan. The discovery left both the streamer and his audience completely stunned, which is half the fun of watching the clip. The minigame itself feels like a nice callback to Disney's Tarzan, featuring rushing water, twisting roots, and plenty of jungle scenery.
I remember.
Of course, the secret would have been
That's
the
a good
worst
game.
level in the game we were all trying to rush through.
This isn't really a secret, though.
Sora's weight.
If you're farming for the ultimate weapon, you gotta...
Hidden bosses are cool and secret cutscenes are great, but sometimes the strangest discoveries are the most
I'm gonna
memorable.
re-download
Tucked
Kingdom
away in
Hearts after I get out of this
first
cave.
district is a tiny detail that lets players check Sora's weight. Inside Huey, Dewey, and Louie's shop, a scale sits between the counter and the lower entrance. Don't stress, it's not for you. By switching to first-person view and looking at it, you can see exactly how much the Keyblade wielder tips the scales. It serves absolutely no gameplay purpose, which somehow makes it even funnier. Sadly, Donald and Goofy don't get the same treatment, so we'll never know what a talking duck weighs. I assume his weight doesn't often go down. I hate myself. Play as Cloud, kinda. For some fans, simply playing as Sora was never enough. Over the years, players have dug through Kingdom Hearts looking for ways to control other characters, and one of the more interesting discoveries involves Cloud from Final Fantasy VII. Through the use of cheat devices and modified game codes, players can actually take control of him during the Hercules Cup. It's not exactly a polished feature. Cloud can't run around normally and doesn't have access to abilities like high jump, but on the bright side, he gains a pretty hilarious advantage, the ability to fly and attack enemies while floating through the air. It's a rough but entertaining experiment that shows just how creative the community can be with the codes they've been given. Changes depending on how you play.
The hunter lured them there. It was his lustful follow that was the bait.
Not every choice in Kingdom Hearts leads to a different ending, but the game does sneak in a few small changes depending on the order you tackle its worlds. One easy-to-miss example happens after wrapping up the story in Deep Jungle. A cutscene plays featuring several bad guys as an actual threat rather than a collection of familiar faces. Here's where things get interesting. The princess shown at the end of the scene can change. Most players see Snow White, but those who unlock Wonderland first will instead be greeted by Alice. It's a tiny detail, yet a neat reminder that the game's progression isn't completely set in stone. Speedrun hack. Here's a speedrunning strategy that sounds completely backwards. Instead of rushing through Kingdom Hearts as fast as possible, you can actually spend 100 hours doing the exact opposite. Take your time, explore every corner, fight optional enemies, and generally play at the pace of someone with nowhere to be. Once you hit 100 hours, head to the final boss. Thanks to a quirk in how the game tracks time, defeating the ending within 15 minutes of 100 hours makes it appear as though your entire adventure was completed in under 15 minutes. The result, the coveted Speedster trophy lands in your collection despite your marathon playthrough.
That's funny. I remember grinding for the Platinum Kingdom Hearts. It is a struggle. Kinda. I mean, after you play the game for years, it's not, but grinding for the ultimate weapon is always...
The Kingdom Hearts series loves hiding meaning in plain sight, and the character names are one of the best examples. At first glance, Sora, Riku, and Kairi just sound like cool names, but they actually connect to the natural world. Sora translates to sky in Japanese, Riku is associated with land or earth, and Kairi's name comes from the sea. Put those three elements together and you've basically recreated the environment of Destiny Islands itself. It's a clever little detail that many players missed during their first playthrough. The trend didn't stop there either. Years later, Kingdom Hearts Birth by Sleep introduced Terra, Ventus, and Aqua. Their names come from Latin and translate to earth, wind, and water respectively. But this list isn't about them, I just had to mention it because it's sick. Get off my back.
Then ours is just a little piece of something much greater.
Original clothes. It's funny to look back at the earliest footage of Kingdom Hearts because Donald and Goofy almost look like they'd wandered in from a completely different game. Before release, both characters appeared in the clothes fans knew from the classic Disney cartoons. Goofy sported his usual green hat and blue jeans, while Donald was dressed in his familiar sailor outfit. The decision was made to give them designs that better match the fantasy adventure setting. The knight-inspired outfits seen in the final game ended up fitting the Keyblade quest much better than their everyday cartoon